So let's have a look at the product rule. So the product rule is similar to the chain rule in the sense that it is dealing with a particular type of function. In this case, we're interested in functions that look like this, where u is a function of x and v is also a function of x. Okay? So you can think of y is equal to u times v, or you can think of y is equal to f of x times g of x. And it's different, right, from the chain rule. Why? Because in the chain rule, we were looking at functions of functions. In this case, we're looking at two functions just multiplied together. What did that look like? Well, let's imagine a function that looks like this. 3x squared minus 2 times 5x to the 3 minus 7x. Right? So if we had two functions that looked like this, how could we differentiate it? Well, we don't currently have a rule, but now we do. So the two ways we can think about it, depending on whether we're using Leibniz notation or function notation, doesn't make much of a difference, right? Because just in the back of your head, remind yourself that these two things are true, right? Every time you see a u, that's f of x. Every time you see a v, that's g of x. So let's split this up into two bits, and let's do it using function notation and using Leibniz notation. So just to finish off with the function notation, let's set h of x is equal to y. So we've kind of got these mirroring partners here. It's going to work the same, but it's just going to look a little bit different, right? So in Leibniz notation, to work out the derivative dy dx, we take the first function and multiply it by the derivative of the second function, dv dx, and then we add to that the second function multiplied by the derivative of the first function, du dx. Alrighty, so it's actually a rather simple thing to work out. You just got to do two derivatives and then combine them in a particular way. It's very similar in function notation. We take h dash of x, we get it by taking the first function and multiplying it by the derivative of the second function, and we add to that the derivative of the the second function times the derivative of the first function. And so we get this partnership that looks like this, right? Which matches the flow on this side. And as just a reminder, h of x is the same as y, and dy dx is the same as h dash of x. Alrighty, so we're using these different notations to do the exact same calculation. But essentially, a way to think about it in words is this. The derivative, first function times the derivative of the second plus the second function times the derivative of the first. Alrighty, and so when we look at that visually, the first function times the derivative of the second plus the second function times the derivative of the first. And that matches for both functions, and both in function notation and in in Leibniz notation. So let's have a look at a few examples. So if I have a function, let's call it y is equal to x squared plus 3x 4x to the 5 minus 2x. Question is, how do I derive it? Well, first of all, let's set up some notation. U is equal to x squared plus 3x, and v is going to be equal to 4x to the 5 minus 2x. Alrighty, so this is going to be my first function, this is going to be my second function. Let's derive both. Du dx is equal to 2x plus 3. dv dx is equal to 4 times 5 is 20x to the 4 minus 2. And now we can substitute straight into the formula. So dy dx is going to be equal to the first function times the derivative of the second plus the second function times the derivative of the first. Alrighty, so u is equal to x squared plus 3x. The derivative of the second is going to be 20x to the 4 minus 2 plus v times du dx. Now I'm just going to do some algebra to simplify this. So we've got x squared times 20x to the 4 is going to be 20x to the 6. X squared times minus 2 is minus 2x squared. 3x times 20x to the 4 is 60x to the 5. And 3x times minus 2 is minus 6x. Plus, let's expand the next set of brackets. 4x to the 5 times 2x is 8x to the 6. 4x to the 5 times 3 is going to be 12x to the 5. Minus 2x times 2x is minus 4x squared. And minus 2x times 3 is minus 6x. Looking for like terms, we've got 28x to the 6. Looking for more like terms, we've got plus 72x to the 5. Looking for more like terms, we're going to get minus 6x squared. And the final bit of like terms, and last like terms. Alrighty, and so from there, we have now worked out the derivative function, right? So this is how to use the chain rule. Let's look at another example of the product rule. So if we've got h of x is equal to 3x minus 2, 5x squared minus 3. Alrighty, so first of all, let's work out our function. So we can have f of x is equal to 3x minus 2, g of x is equal to 5x squared minus 3, f dash of x is just equal to 3, g dash of x is equal to 10x. The derivative of h is equal to f times g dash plus g times f dash, all of those of x. We're just using some shorthand, and we get 3x minus 2 times 10x plus 5x squared minus 3 times 3, right? And now we can just expand all of this and work it out. So we're going to get 30x squared minus 20x plus 15x squared minus 9. And we've got only one set of like terms, so let's collect those. And there we go. There's a few applications of the product rule.